Okay, so welcome everybody. In the last class, we have seen the functionalities or how the current and voltage behaves in the Josephson junction, right? So we explicitly considered one superconductor, and then there is normal metal, or usually it is insulator, and then there is another superconductor. Okay, so SNS junction, superconductor, normal metal, and then again superconductor junction. So where we have found that in presence of magnetic field, if we have some applied magnetic field in this whole setup, okay, some magnetic field, let's say, into the plane, then we had the expression of current, which was something like sine delta 0, where ICB, critical current, which depends on the magnetic field, was IC0, critical current at the zero magnetic field, and then there was sine phi pi phi by phi 0 by pi phi by phi 0, where phi was total flux through the junction, and phi 0 is the usual quantum of magnetic flux, h by e. And delta 0 was the phase difference. So we have that current distribution, which looks like ICB, and if we plot it as a function of phi, this phi, then we had some diffraction pattern type thing. Similarly, in this part as well, this should be symmetric. Okay, so the amplitude will start decreasing as we increase phi, the magnetic flux, and this will be 0. This should touch 0 axis at phi 0, then 2 phi 0, and then 3 phi 0, like this. Okay, so at each integer value of magnetic flux in units of quantum of flux phi 0, that critical current is 0. So that was the case for Josephson junction. Now we will see. Let's say we have two Josephson junction clubbed together, which we call squid. So we have, so let's say let's draw a circular squid type thing. So we have circular so this is one part of the superconductor SC, and this is another part of the superconductor, and we have connected it to the circuit where we are sending electricity or current, and then in this part there is insulator, this part also. Okay, so insulator. So effectively, if we think, then if we divide it, then uh, this part, the total part is one squid. So this is one squid, sorry, one Josephson junction, and the upper part is another Josephson junction, right? So let's say this is first, and this is second Josephson junction. So this type of geometry or this type of clubbed Josephson junction is called squid. Okay. So in this portion there is nothing. This is vacuum. Okay. And where there are two Josephson junction on each side, and in the middle path we send current. Now again, so similar to the previous case, we'll apply a magnetic field in the uh, junction. So let's say we have applied magnetic field which points inward to the sample. Okay. So B. Okay. And we assume that there was a phase difference between the wave function on each side of the superconductivity. So here we assume that the phase difference is delta 1, and in this case, or let's say this is delta 2, and in the below side this is delta 1. Okay. This is delta 1. So this I, here also comes I, right? So then we can write I equal to, so what will really happen? I have current I, and then in this way there will be, let's say, I1, and in this path there will be I2, right? Then they will again add up, and which will give rise to I current. So current I will be I1 plus I2. Okay, so this is, I am assuming second reception, so it is better to denote as I2 and then I1. So for each case we can write that IC B sine delta 1. So we are also assuming that this both the Josephson junction first and second are identical to each other. That's why ICB is identical, but we assume that the phase difference might be different. Okay. So then ICB sine delta 2, right? So this we can just divide, or sorry, or further explicitly written as 2ICB sine delta 1 plus delta 2 by 2, and then cos delta 1 minus delta 2 by 2. This is just the use of sine x plus sine y property. Okay. Now we consider a loop. We consider a loop which is substantially away from this circuit. Okay. So let's say we have considered a closed loop like this. Okay. So then in this case, in our previous lectures as well, we have seen that the flux can be counted or calculated from this simple relation grad phi dot dl over the closed loop C. So let's assume this closed loop is C, and then which will be 2 pi by phi 0 total flux. ds is the area, elemental area for this closed loop. So total area is this the surface area of this closed loop. Okay, and grad phi is the phase difference. So here we can directly say that the phase difference is simply delta 1 minus delta 2, right? Because so here we have assuming this is delta 1 and this is delta 2. So the phase difference is simply delta 1 minus delta 2, and then 2 pi by phi naught. This we assume to be phi. Okay. So if we plug that in this equation, then we will have 2 IC of B sine delta of average. Delta average is delta 1 plus delta 2 by 2, and then cos 2 pi phi by phi naught by 2, right? So if we explicitly write the expression of ICB, which was IC0, so critical current at the zero magnetic field, and then it was sine pi phi prime by phi 0. I will explain what is phi prime, then pi phi prime by phi 0, and then there is cos 2, sorry, there will be no 2, 2 will cancel out, pi phi by phi 0, and sine delta bar, right? So what is phi prime? Phi prime is the magnetic flux through the each Josephson junction. So phi prime is this the magnetic flux passing through this area, this particular area, okay, which is the Josephson junction area. Okay, so this area we have considered that in both the uh, upper and lower Josephson junction, it is basically the same, right? Two identical Josephson junction are merged to form a squid. So phi prime is the B, and this, let's say, area AJ, area of Josephson junction. So this is phi prime, okay, and phi is the B times total surface area, which is enclosed by this closed loop C. So the entire area, this this entire area, okay, which is S. So that is the difference between phi prime and phi. So if we have considered only single Josephson junction, then we would have encountered with this only, okay, not this case, right? So now let's see what is the form of uh, current as a function of magnetic field. Let's see. So ICB, initially when there was only one Josephson junction, then we had something like this, right? Now there will be additional thing. So when we have this kind of curve, what we essentially have is that this was the form, right? So this was ICB, and this was the form with phi. Phi with phi and magnetic field, we have same type of graph because phi is linearly proportional to B, right? Phi is just the B times the area. So there was only sine pi phi case, okay? And here phi was Josephson junction flux, okay? So so that is the envelope thing, and then there is extra thing here, uh, which is cos phi by phi 0. This is independent of magnetic field, independent of B. So magnetic field dependent term is these two. Where this term gives rise to this big envelope, and this will give rise to, or the when combined with this two term, this will give rise to very small oscillation pattern. So this will be something like here again 0, then again it will rise. So something like this. Okay. So if you write it explicitly, this minima, this bigger envelope minima, this is the minima occurs due to the minimum in the function sine pi phi prime by phi 0 by pi phi prime by phi 0, right? And this minima within each big envelope, there are many minimas, right? This minima occurs due to minimum in the cos pi phi by phi 0. Okay. Again, it's a reminder. Phi is the total enclosed flux. Sorry, total enclosed flux within the big circular loop C. This is the total enclosed flux by the Josephson junction, which is very small. Okay. Now, now the usefulness of this type of curve or squid when two Josephson junctions uh, are clubbed to form a squid is that so let's say I have some magnetic field in some places, okay? So that's why we use the squid to measure the magnetic field. Extremely, it can measure extremely small magnetic field. Let's say I have some area. Uh, there are some magnetic field here. Now I bring in the squid, the whole setup, and pass the current and measure the current. Okay, as a function of magnetic field. I am also so let's say I have some magnetic field already there, which may be constant or may not be constant. Okay, so then if we measure that current as a function of this flask phi or b, then we will see that this type of minima will occur whenever the flux through the Josephson junction is, this will be phi 0, here 2 phi 0, like this, okay, here 3 phi 0, where phi 0 is h by e. H is Planck's constant, E is electronic charge. So this, so by, so we know that whenever flux is becoming phi 0, okay, flux through the Josephson junction is becoming phi 0, then we have a minima in the current distribution. From this, we can actually measure the magnetic field passing through the, uh, so let's say this is a Josephson junction area. So from this, we can measure the magnetic field present in this area. Okay, we have Josephson junction like this. So it turns out if we do calculation for a typical system where we have, so typical system means the lab में हम जो जिस the size that we use for squid study, which is around, it's a very small thing. This type of circular squid, we have a radius of around only 1 centimeter. Okay, so this is the typical size. Then the calculation shows that we can measure this 10 to the power minus 1 Gauss amount of magnetic field. This is a very small magnetic field, by the way. It means zero point 0.1 Gauss is quite small magnetic field. Okay. So this was the Josephson junction story. If we only had the Josephson junction, now we have the squid, two Josephson junction, where the current will form like this. Okay. So by the way, so let me write it clearly. So this is for single Josephson junction. Okay. This blue curve is for squid. Okay. So this squid current distribution actually follows the envelope of the single Josephson junction, but it has many other minimas and maxima in between each interval, right? And it turns out that this, sorry, this minimum magnetic field, this minimum magnetic field is much smaller. So it's kind of, let's say, 10 to the power minus 8 uh, Gauss. So how can we say that? Because this is the minima of occur due to minimum in cos phi by phi 0, right? So when cos phi by phi 0 equal to 0, it is 0 when n pi by 2, right? Equal to cos n pi by 2. So then we can write, let's say, for the lowest case n equal to 1, then we will have phi equal to pi by 2, here also pi by phi 0. So phi equal to phi 0 by 2, right? Now phi is what? Phi is the total area of the squid or around that, right? So I have a squid like this, right? And I have considered that, let's say my uh, circular path C is like this, right? So it will be of the order of radius of the squid, and we in the experimental lab we took radius to be 1 centimeter. So from that we can get estimate of the magnetic field present in some places into the area. Area, let's say pi r square. Area will be of the order of pi r square because this is pi r square area, right? But we are talking about this whole circular loop. So, but of the order of this will be like phi 0 by 2. So if we calculate this, this will be around 10 to the power minus 8 Gauss. So how much sensible you can already see. So Simple Josephson junction was able to detect 10 to the power minus 1 Gauss around, this is approximate numbers, but whenever we form a squid with the two Josephson junction, we are able to measure 10 to the power minus 8 Gauss magnetic field. So magnetic field in terms of Gauss is already quite low, and then we are going 10 to the power minus 8. So this is a very extremely sensitive probe of magnetic field, and as well as magnetization also. It can also measure magnetization because essentially B is equivalent to M, right? You can write B equal to M0 H plus M in a magnetic system. So here this is the external applied magnetic field, and this is the internal magnetization. Right, so this can prove both magnetization as well as externally applied magnetic field. So that's why it is a very useful device. Okay, so let me move to the next thing. Okay, so there is another important thing in the squid, which is the IV characteristic curve. This is voltage applied in the system or squid. This is, let's say, current or critical current. So what really happens is that up to a certain point, so there is voltage is precisely zero, and then it starts developing. This is IC0, let's say, critical current at the zero magnetic field. Now, if we apply magnetic field, then the critical current is less. This is, let's say, ICB. Okay, something similar, something like this happens. Okay, so next problem. So next problem is related to the again normal metal and superconductor interface. So let's say I have a normal so this side is superconducting, this side is normal. So and I have applied magnetic field, let's say. So what will be the magnetic field penetration? So in the normal side there will be magnetic field as usual, but Once I am inside the superconductor, it will be decreasing, right? It will start decreasing, and this will decrease with a length of lambda L, let's say, London penetration rate. And the wave function, superconducting wave function, within the superconductor, the wave function is almost constant, let's say some value, constant well within the superconductor. And as we uh, come across the normal interface, this will start decreasing, and at the junction it will be zero. Right? And the characteristic length for this is, let's say, xi, which we sometimes call Ginzburg-Landau length parameter. So in this case, we have considered that xi is greater than lambda L, right? So I have solved this in last tutorial, I think. This is essentially we are considering 1D case. So the psi x superconducting wave function will be psi 0, and then tan hyperbolic x by root 2 xi. Okay. So psi 0 square equal to the density, superconducting Cooper pair density basically. This is Cooper pair density. Okay. And why this makes sense, let us see that. So let's say we have a junction at x equal to 0, right? X equal to 0, there is a junction. So when x goes to infinity, then tan hyperbolic x, this is a general formula we can actually easily see or check that tan hyperbolic goes to 1. So that means psi of x at x tending to infinity, it's psi 0, which makes sense. And psi 0 doesn't depend on x, right? So if you are very or well within the superconducting material, we have a constant wave function, psi 0. But as we approach the junction thing, normal and superconductor junction, interface rather, then tan hyperbolic is less than 1. Okay, tan hyperbolic is less than 1. So tan hyperbolic x is less than 1. That means psi x also decreases as x decreases. So that is the, so that then that means that this behavior or the function psi x equal to psi 0 tan hyperbolic of x by 2 xi makes sense, right? Okay, so in terms of Ginzburg-Landau, Ginzburg energy is given by Ginzburg-Landau free energy for our case is given by 0 to L. Again, we are working in one dimension. Okay, so let me write it. 1D 1D normal superconductor interface. So that's why we're integrating up to 0 to L, and then dx by L. We are assuming alpha psi square plus beta by 2 psi to the power 4 plus h bar square by 2m star psi prime square, right? That was the free energy when there was a non-homogeneous wave function. So this part is free energy, so lambda of free energy. And this is the extra term that comes into the picture when we talk about Ginzburg lambda of free energy. Total Ginzburg lambda of free energy. Okay. So in the Ginzburg lambda of free energy, we allow that the wave function may not be precisely constant throughout the system, but it can vary with the uh, x or any other spatial variation, right? And we also had that psi 0, which is equilibrium case, psi 0 is square equal to alpha by beta. So these are actually detailed. I have calculated in detail in probably lecture 2 or 3. So this is equilibrium value at large x. Large x because within the again, so if you are well within the superconductor, that means psi 0 is the constant thing, and that psi 0 is given by the lambda of free energy minus alpha by beta. And alpha we considered alpha T minus Tc, and beta is essentially constant, not a function of temperature. And also remind that whenever we talk about this Ginzburg theory or Landau theory, we are essentially in the regime of less than uh, transition temperature, but we are not really very far from the transition temperature. Okay? So any free energy construction of Landau or Landau Ginzburg, these are valid around transition temperature, but below transition temperature. Okay, it is not that T is much less than Tc. This is not valid. In this regime, the Landau theory or Landau-Ginzburg theory is not valid because then the order parameter psi will be larger, and this is essentially free energy expansion because in this case we stopped at 5 psi to the power 4, but there are no reason that we could not have psi to the power 6 plus psi to the power 8, something like this. Okay, because it is small, size is small, which becomes when we are around transition temperature but below transition temperature, then it is valid. Also note that we will not consider psi cube, psi to the power 5. This type of term are not considered because the superconducting system have a U1 gauge symmetry. U1 gauge symmetry. So this is a slightly complicated thing and more advanced thing, which restricts that the odd order parameter, which is psi cube, psi to the power 5, cannot be there. Okay, so that's why we would never consider psi to the power 3 and 5, so on. Okay, so in this case, okay, so for homogeneous system, for homogeneous case, we have F equal to homogeneous. This was precisely the Landau, right? For homogeneous case, we will apply Landau, and for non-homogeneous case, we'll apply Landau. Non-homogeneous means size not really purely constant. It can have some variation with x. So this will be alpha psi square plus beta by 2 psi to the power 4. So the difference delta F is F minus F homogeneous is given by Bx by L alpha psi. Okay, so for our convenience, let me write it like that. This is psi 0 fx, okay, where fx is tan hyperbolic x by root 2 xi. I have just separated the constant part and the x dependent term. So then we can write it as psi 0 square and then f square x minus 1, right? Because in this case, homogeneous case, psi is only psi 0, okay? So in this case, psi is only psi 0 because fx equal to 1 effectively. Then beta by 2 psi 0 to the power 4 f to the power 4x minus 1 plus this will be simply h square by 2m psi prime square, right? So if we take out that psi 0 constant part outside, dx by L, sorry, so L is because we are considering the free energy density. So lambda free energy is the actually it is the free energy density. So this was free energy, and then density is L because we are considering simply 1D case, and then it is integrated with x, which will give me again free energy. So if we common the psi 0 square, it will be alpha fx square minus 1 plus beta by 2 psi 0 square f to the power 4x minus 1 plus h bar square by 2m fx square, right? Okay, so if prime x square rather, if prime x, now we will use two, so we'll introduce two just parameter for our convenience. H c square equal to 4 pi alpha square by beta, and then xi square, Ginzburg-Landau length parameter. We have already explicitly calculated minus h bar square 2m star alpha. You may think that why it is negative, right? This is even a square of a length. It is not really negative because h bar square 2m star alpha 0 Tc minus T, or let me write it more directly. So this was minus and T minus Tc. Now whole theory of Landau and Landau-Ginzburg, I just said a while ago, that is valid for T less than Tc. That means this is already negative and here is negative. So overall it is definitely positive. Okay. Okay, so we have introduced these two parameters. Then we can write just simple calculation h square by 4 pi. This is, let's say, 0 to infinity integration of 1 minus f square x square plus xi square f prime x square. how did we get this? We just use these two definition and added these two things to write it as a full square, 1 minus f square x whole square. Okay, and we all have also used psi 0 square equal to minus alpha by beta. When we write it like minus alpha by beta and then put it there, then we can have this form xi square. Or let me do it actually, since there are 2-3 step jumps. So first of all, we will write psi 0 square equal to alpha by beta. Then, so L is already on the left hand side. So dx alpha f square x minus 1 plus beta by 2. Psi 0 square is again alpha by beta minus alpha by beta f to the power 4x minus 1 plus h bar square by 2m and then f prime x square, right? So if we take this alpha to be out, so then it will be minus alpha square by beta integration dx, and let's say we also put that minus sign in within the bracket. So 1 minus f square x, this will be plus 1 minus f square x plus, so this alpha is already gone, this alpha, this beta and this beta will cancel out. Then we have only half f to the power 4x minus 1, and then there was extra minus here, so minus h bar square by 2m star, then alpha we took common, so alpha will be there, f prime x square. Okay, so now we can write this alpha square by b equal to hc square by 4 pi, right? So hc square by 4 pi integration dx, this side it is L into delta F. Delta F is nothing but this difference in energy between homogeneous and inhomogeneous case. So this will be so if we take half common, so okay, which we have half, let me see. So f to the power 4x minus 1 or it will be, so this 1 and this minus half, right? So this will again be only minus half. So, so this will be 1 and minus square x 2, right? Sorry, this will not be prime, rather f square, and this should be plus. So just a side mistake. Okay. Okay, so this will be actually plus up, okay? Because from here this is 1 and from this 2 there is minus up, which will be plus up. That was the mistake. And then minus h bar square by 2m star alpha alpha f prime x square. This will be hc square by 4 pi integration over dx. We can write this whole thing as 1 minus fx f square x whole square minus, now we need to do f prime x, okay, where f of x was tan hyperbolic, sorry, x by root 2 xi. So if we can do this simple tan hyperbolic derivative, it will be f prime x equal to 1 minus tan hyperbolic square x by root 2 xi, right? Okay, so this is the f dash x, so which we can again write it as 1 minus fx square by root 2 xi. Okay, so then we'll write it as f square 2m star alpha, then f star x square it will be 1 minus f square x square by root 2 xi square. Okay, so I think there are still a negative sign extra here. or not really? Okay, fine. Because xi square itself contains extra negative sign, 2m star alpha, right? So this will be L delta f equal to h square by 4 pi dx half 1 minus f square x whole square, and then plus xi square using this formula, 1 minus f square x whole square by 2 xi square. So xi square cancels out, and it turns out hc square by 4 pi integration of dx only 1 minus f square x square, right? So this is the extra free energy. Now if we try to explicitly so h square by 4 pi integration 0 to infinity dx can we do it analytically or we need to do numerics? That's what I'm thinking. Okay, let me try. Not sure we can do this, but this is 1 minus f square x. What we really had is 1 minus f square x by root 2 xi was this term f prime x, right? So f prime x. Now let's apply this. So I'll write one part of this. So we can write this on f square x and then another f square x, right? So h square by 4 pi 0 to infinity. I'll write this using this. So it will be root 2 xi dx f prime x 1 minus f square fx, right? So hc square by 4 pi into root 2 xi 0 to infinity dx f prime x and 1 minus f square x square, sorry, single. Now let's see fx or f prime x equal to df dx, right? So then we can write it as hc square by 4 pi root 2 xi. This term, this two term will give me df, right? Using this, f prime dx will be dx. So then df 1 minus f square x. So what will be the limit? So if x goes to 1, x goes to infinity, in the limit x goes to infinity, and if x goes to 0, x goes to 0 limit, right? So 0 to 1. Then we can easily do this integral and show that this will be h square root 2 xi by 4 pi into 2 by 3. This is nothing but 2 by 3 because uh, this will be 1 and then f cube by 3. Sorry, f 0 to 1. So this will be 1 minus 1 by 3 equal to 2 by 3. Right? So this is the amount of extra energy uh, for a inhomogeneous psi x. Okay. So Landau-Ginzburg, if we use Landau-Ginzburg energy, then we have the extra free energy. Delta F is greater than 0. Here all are positive numbers. That means F inhomogeneous is greater than F homogeneous. That's what it tells. So in the inhomogeneous case, we have more free energy, or basically free energy has increased. So the question might just simply be there, like calculate the extra amount of free energy that is acquired when we consider the inhomogeneous free energy of Landau-Ginzburg theory rather than using Landau theory. Okay, so next problem. Just a second. Okay, so next problem is on just there may be question which may ask that calculate the extra amount of Gibbs free energy which is there in a superconductor than a normal state. let's say. Or they can also tell us to calculate the amount of extra energy of a superconductor at some particular temperature uh, at the zero magnetic field, and then there is a finite magnetic field, right? So whenever we apply magnetic field, the superconductivity starts destroying after a certain value of magnetic field. So it can be, they can ask this basically. So for this, uh, we we have to start from CV, which is the specific heat or heat capacity. CV for a normal, let's say normal system is gamma T plus AT cube. This is for a normal metal, sorry, normal metal, let's say. So this gamma T contribution comes from the electrons, and then this T cube proportional uh, portion is due to phonons of the system, of a lattice system. Okay. Now CV is simply TdS dt, right? Where S is the entropy. And Gibbs free energy is related to dG is minus S dt minus VdP, which is simply minus S dt. We're assuming there is no pressure, no magnetic field as of now at least. So let's first calculate for a normal system. For a sorry, normal metal, we'll calculate G, Gibbs free energy. So then we have CV equal to TdS dt equal to, or rather we first calculate S, so that we have this S and then dt. So S will be CV by T dt, right? Integration. So this will be sum S0 plus gamma T plus again A 1/3 T cube, right? The simple integration of this term. So now assume, this is just the assumption, or we can equally write that S minus S of 0 is nu S, right? So just S0 is the constant independent of temperature. So S equal to gamma T plus 1/3 A T cube. So this is a function of temperature. Now S equal to minus del G del T at constant pressure and constant or no magnetic field is equal to 0. This will be, that means G of T, again integration, minus S dt. So that means G of T will be minus half gamma T square plus 112 A T to the power 4, right? So again, there will be some constant which will again write it as this term, constant term. So Gt minus G0 equivalent to Gt, which will be minus half gamma T square plus 112 A T to the power 4. Okay, so this is equation number 1. Now consider a superconductor. Consider a superconductor with applied field to be H. Okay. Since superconductors are perfect diamagnet, then magnetization in the system will be minus H by 4 pi, right? In the CGS unit. CGS unit. Because within the superconductor, B will be 0 and B is H plus M. In the SI unit, it is mu 0, but in the CGS unit, it is equivalent to 4 pi H plus M. From this, we can say that M is, 4 pi will be with the M, H plus 4 pi. Okay. And whenever we apply magnetic field, there will be change in also Gibbs free energy, which will be in SI unit. If we talk about mu 0 M dH, simply M dH, okay, or in SI unit, here M will be simply minus H, right, from this equation. So it is important to know both the unit, because we really do not know in which unit they will give. So this is for the superconducting case. We are considering superconducting case. Now if we integrate this, BGS equal to minus mu 0 M dH. And M is minus H, so plus mu 0 H, sorry, H dH, right? So, sorry, this was H equal to 0. Let's say I have H equal to 0 and I have applied some H equal to H amount of magnetic field, or HC, let's say, magnetic field. And so this, after integration, this will be superconducting, gives free energy at some magnetic field Hc minus Gh at 0 magnetic field. Then this will be Hc square by 2, right? So this is, let's say, equation 2. Now, what we know from let's say GST Hc equal to GNTHc. Why this happens? So this is for superconductor, this is for normal, right? This happens because at Hc, critical magnetic field, the system starts becoming normal, right? That is the transition. So I had a superconductor, I start applying magnetic field and start increasing the amount of magnetic field. So at H equal to Hc, the superconducting becomes normal system. Okay. So that means the Gibbs free energy for these two systems at a particular temperature, whenever it reaches the critical magnetic field value Hc, the Gibbs free energy becomes same. Okay. Now let's assume that normal metal is magnetic, sorry, non-magnetic. So if we assume that the normal metal is non-magnetic, then we have 0 to Hc dGn, n for normal, minus mu 0 0 to Hc mdh, right? So if this is non-magnetic, then m is simply chi h. Chi is the magnetic susceptibility, magnetization per unit applied magnetic field. So this will come out as mu 0 chi hc square by 2. Okay, so this will be GnHc at some temperature minus N at some temperature h equal to 0. Okay. So that means now for a here there will be extra negative sign. For a non-magnetic material, chi is 0, right? So magnetic susceptibility always almost tends to 0 for a non-magnetic material. So this gives us GnTHc equal to GnP at 0 magnetic field. Okay, so this is 3. That means that for a normal metal, Gibbs free energy at normal non-magnetic metal, Gibbs free energy doesn't increase after applying the magnetic field, which is really understandable, right? Because for a non-magnetic normal metal, there is no magnetization becomes induced in the system after applying magnetic field. So we can almost negligible that uh, thing. So there will be no increase in uh, Gibbs free energy. Now look at the equation 3 and this equation. Okay, let me put it equation 3 and this is equation 4. So from equation 3 and 4 we have G GSPHC equal to GNPHC equal to GNP0, right? So 5. So Gibbs free energy for a superconductor at critical magnetic field is equal to the normal metals Gibbs free energy at the superconducting transition magnetic field, which is again equal to the normal metals Gibbs free energy for the zero magnetic field. Now we will use this equation. GNTHC is essentially equal to GSTHC, right? So that means we can write GSTHC minus or or we can write it differently. We'll write it as GNT0 from this two, GNTHC and GNT0 minus something is not, just a second, we can write GNTHC equal to GSTHC. Okay, no. So we'll not use this equation, rather this equation, equation 2. What was our equation 2? So, okay, so we'll use GHHC equal to GNT0. GNT0 minus GST0. So here G means, sorry, 0 means actually magnetic field 0, not T equal to 0, okay? This will be mu 0 C square by 2. This is the final equation. So this shows that even at T equal to 0, T equal to 0, oh sorry, H equal to 0, H equal to 0, no magnetic field case, the GNT0 is greater than GST0, right? So, because this is always positive, this term, this term is always positive. So, superconducting state have lower energy than normal state at H equal to 0, which is physically also consistent, because if it have a lower energy, then it will be stable. Otherwise, it will be a unstable case. So if we plot this, there will be no plot. This is temperature is also constant. Okay, so that was today's class. I think this is also the last class. Usually they also give another extra class just to clear the doubts and other things, but they have not mailed so far. I have nothing extra to do that, so let's stop here. Thank you for joining. Or if you have any doubts, let me know. Any doubts?
No, sir.
Okay. Okay, so let me stop. Or if you have any doubts even, then You can actually mail me. I hope you know my mail address, but still, so I'm writing it in the chat box.
Mail, sir.
Yeah, so this is my email address. So if you have any doubts, you may ask me. Okay. So I'm ending the meeting. Thank you for joining.